Okay, we are going to look at number 21. As always, I want to remind you, this is one that we have seen before. So at this point, if you have not yet done this problem, stop this video, go and do the problem, then come back and watch it. Okay, let's see what we got. So we have the volume of a spherical balloon, right? So it's a hot air balloon, right? And it's expanding as it's getting hotter. The radius of the balloon in feet is modeled by a twice differential function, r, of time t, where t is measured in minutes from time 0 to 12. Let's see. Oh, sorry. Where t is measured in time. From 0 to 12, it is concave down. Okay, I'm gonna highlight that. I feel like that's gonna be important. Important? I don't know. So then let's see, the table above gives selected values of the rate of change of r. So this is important. I want to remind you, whenever you look at a table graph or anything like that, you have to say, what am I looking at? Am I looking at a position, velocity, or acceleration? This is a velocity function, right? Because we're looking at r prime. So we're looking at the rate of change of the radius, not the lengths of the radius. Okay, and then they gave us a point. Right, I'm just gonna, so in summary, they kind of gave us this point, which we may or may not need. Well, I guarantee we're gonna need. There's no way we're not gonna need it. If they give it to us, we need it. So anyway, at time 5, the radius is 30. Okay, and then they get, I didn't put it down here, but they did give us the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. Okay, so we are, let's see, part A, estimate the radius of the balloon, right, when t equals 5.4 using the tangent line approximation at t equals 5. So this is, we did this just a few days ago, right? We're doing a linearization thing. So in this case, we are writing the equation of a line, and then we're using that line, right, to approximate a value. So let's do it. So in order to write the equation of a line, you need two things. You need a point, which there at time 5, so that's the point 530. That's where that point 530 came up right here, right? And we need the slope of, we need the rate of change of the radius, or the slope of that line at time 5, which I think you guys agree. Let's get rid of that. We can put that in, and that's going to be equal to 2.0. Okay? So what is the equation of our line? Our equation of our line is y minus 30 equals, what is the slope? 2 times x minus 5. So I get y equals 2 times x minus 5 plus 30. From here, we just evaluate this at that the number they want us to do it was 5.4. T equals 5.4. So actually, I know I've been using x's. It doesn't matter, but technically, right, we should be using t's. I don't think they would take off for that, but it's probably a good idea to use the variable that they had. So we had 2 times 5.4, minus 5 plus 30. Okay, so that would be our approximation. Did they ask us to use units? Nope. But they did ask, is your estimate greater or less than? So here's how we answer this question: whether this is whether our thing is greater than or less than. It comes down to the fact that they told us that our position function, right? The graph of r is concave down. So kind of imagine for a second. So imagine you have this graph, right? In order for it to be concave down, it's got to look like that. And remember, the way we know something visually is concave down is that any tangent line to the graph is going to lie above it. So in other words, right, if I'm coming up with an equation for a line, for example, this line right here, the tangent line to this graph, that tangent line is going to be above it. So any point that we evaluate, like 5.4, if I evaluate it, it's going to be greater than or equal to the position value, right? Let me just kind of zoom in here really quickly. So if I'm evaluating it, let's say, and I didn't do a very good job of this, but let's say this is 5 and this is 5.4, right? So I'm trying to evaluate this point right here on the graph, but my tangent line lies above it, right? So I'm getting that point with the arrow out of it. But again, because it's concave down, the tangent lines lie above. So when we evaluate numbers, we evaluate values for that tangent line, we're getting an over approximation. So what am I going to say here? I'm going to say, it would be nice to kind of clean this up a little bit, but I will say the value we found is an overestimate, overestimate. Why? Because the function is let's see. I'm going to say the radius function. You see, I would have liked them to like just say r of x or something like that. It would have been nice. It makes the phrasing of this so awkward, but I would say the radius function is concave down. Okay? And that's all we need. You don't have to go through the explanation I did. You just have to say, hey, I'm looking at the concavity. And because it's concave down, right, that implies that all tangent lines would be concave up. Again, you don't even have to say that. You just need to say what I said there. Okay, let's move on to B. Find the rate of change of the volume with respect to time. Okay, so again, we know that our volume is 4/3 pi r cubed. We're going to do this with respect to time. So we get dv dt equals 4/3 times 3 is 4. So 4 pi r squared dr dt. And we are going to evaluate this when t equals 5. So let's plug in our stuff here. So dv dt equals 4 pi. Now be careful. At time t equals 5, we don't have a time t equals 5 here, right? We don't have that. But we do know, right, at time t equals 5, we do know when time t equals 5, I'm struggling here. The radius was 30. It was 30, right? Yeah, the radius is 30. So just be careful of that because you're not plugging in you're not plugging in 5, you're plugging in 30 because they're asking for the radius. So this is 30 squared. And then dr dt at 5, right, is 2. Okay? And that is our thing. And then they ask us to use, what are our units of measure? Well, think about what this is. This is the rate of change of the volume. So this is going to be, I think this is feet cubed per minute, right? Feet cubed per minute. So that's the rate of change of our volume. Okay? Let's keep on going. Let's go find C. Okay, this shouldn't be a surprise to us, right? They're asking us to go evaluate. So I think you guys would agree. We want to go and evaluate this definite integral from 0 to 12. And then they probably also want us to talk about what it means. So I think, and we're going to be using right-hand side rectangles, and we're doing an approximation. So I'm going to let's go and bring that table down so I'm not flipping back and forth. Normally I do that at the beginning, but I did not. That's on me. Okay, let's see if I have room here. Perfect. Okay, so let's see what we have here. So we're being asked to make rectangles with 5 subinterval rectangles using the right-hand side. So if you kind of imagine, this is rectangle 1 where 0 is the left-hand side, 2 is the right-hand side. Then we have rectangle 2 where 2 is the left-hand side, 5 is the right-hand side. And you guys kind of get the idea, right? So rectangle 3, rectangle 4, rectangle 5. Okay, so those are rectangles. Now remember, what are we using? We're using the right-hand side of each rectangle. So let's go and find it. All you're doing is finding the area of each of these rectangles. So for the first rectangle, right, we're looking at the rectangle that has a base from 0 to 2. It's going to be 2 minus 0, which is 2, times the right-hand side. So in this case, I'm using 4, right? 4.0. That's the right-hand side of that one. Then I'm going to go, now that's rectangle 1. Let's go find rectangle 2. Rectangle 2 goes from 2 to 5. So 5 minus 2 is 3. And in this case, I think you guys would agree, I'm using 2 as, that's my right-hand side, so 2.0. Let's keep on going. So we just did, let's just see what we did. So we did 0 to 2, we used 4. We used 2 to 5, which we used 2. Now we're going to use 5 to 7. So 5 to 7 is 2 times 1.2. Then we're going to use 7 to 11, which is 4 times 0.6. And then finally, we are going to go use 11 to 12, which is 1 times 0.5. Okay? That's our value, whatever that is. Do we have to use units? We did. So I think you guys would agree. This is going to be, what were our units? Were they feet? Yeah. So this is in feet. So let's talk about what this meaning is, right? Because it really, this really comes down to the meaning of it. They did want us to, didn't they ask us to describe what it meant? Using the units. Okay, using correct units, explain the meaning. So let's talk about this. So this, the definite integral above, in the definite integral, or we could say, you know what, we'll say, why even say that? I can say this. This, right, we already have our number, represents the change in the length of the radius of the hot air balloon. Now remember, you also have to say over what interval, over what time interval, over, or we can say from, instead of saying over, from time t equals 0 to time t equals 12. Okay? So I do want to remind you, when you're discussing what something means, like a definite integral, when you're discussing what a definite integral means, you have to include the limits of integration in there. You have to say how, you have to include those in part of your description. Okay. D, is your approximation in C greater than or less than this? Give the reasoning for it. So again, we had an approximation, right? This number, whatever this number is, it's an approximation. They want to know, is it greater than or less than? So let's kind of go through the thought process on this, and then we'll talk about it a little more. I want to remind you, this is a concave down graph, right? We were told that from the very beginning. So if we were to kind of just draw a general graph that's concave down, let's say the graph looked like that. That's concave down, right? Imagine what the rectangles would look like, right? Let's make this even more extreme. I'm going to make this even more extreme. There we go. Let's imagine what those rectangles look like. So let's just break this up in like 3 rectangles. So if we break this into 1, 2, 3, right? I think you'd notice if we're using the right-hand side for each of these rectangles, our estimate is going to be an underestimate, right? Because those rectangles lie below it. If we were using left-hand side rectangles, I think you'd agree, we would have an overestimate. So how do we say that? How do we put this all together? So I'm going to say our approximation in part C is, what did we say? It's an underestimation, is an under approximation, or an underestimation, I guess. I don't know. It's not going to matter. Underestimation for this. And what is my reasoning? My reasoning is because the rate of change for r prime of t, right? So now I'm talking about its second derivative, right? So I could say, let's not say the rate of change of that. Let's say, I'll use increasing and decreasing. So because r prime of t is decreasing on that interval. So notice what I'm saying. Notice what I'm saying, because when I'm talking about, excuse me, I keep on repeating myself, but when I talk about r prime decreasing, I'm now talking about, by using the word decreasing, I'm saying, hey, I'm looking at the second derivative, and the second derivative is going down, right? It's decreasing. So I'm saying r prime is decreasing. And what that's so, right? So if you think about it, that means all our slopes to our tangent lines, right, they're all negative. And because this thing's decreasing, that implies that our thing would be an underestimation. Okay? Again, the big thing here, and I know these are hard. I know these. This one was kind of a rough one. The big thing here is to recognize that we're still using that second derivative, right? The big thing is that you're talking about that second derivative. You're saying, hey, look, r prime, which we're given, is decreasing, and therefore, this is our conclusion. Now, I do want to emphasize a couple things. You may be sitting there going, well, I never would have gotten that. How would I have possibly gotten that? Reminder, you're not, there are questions on these things that I call stretch questions. They're a part of a question, or a question that is meant to separate students, right? That is meant to be hard. This is one of those types of questions. You may have said, hey, you may have been able to say, hey, you know what? I recognize this is an underestimation, right? I recognize it because maybe you were able to do something like this. Maybe you graphed it and you got this, but you weren't sure how to put it together again. Well, you probably would have gotten a point for underestimation and probably wouldn't have gotten the point for your explanation. The explanation was rough. Okay? Again, don't fret over the points. There's always going to be, I can't emphasize this enough. There's always going to be parts of questions that you don't understand. And that is okay. Okay, there are some really rough ones. We've seen some really rough ones in this one. That's okay. You're not expected to get 100%, okay? I'll see you in the next video.